Hello, calculus. This is another example of rotating two curves about an axis to find the volume. So, this example, we are going to be rotating again about the x-axis. So that is right here. It's always good to keep in mind our two functions. Again, we have a decreasing exponential function. So that is right here, coming down like that. And then our second function is our x to the 1/3. And that is coming up like this. Okay, so we are again given our limits between 0 and 8. So I'm going to sketch those in right on the graph. Here is, let me make that a little darker, so there's at 0, and then we go out to 8. So I like to shade in that region. All right, so there's our region. Okay, you can see that there is open space between the region and the axis of rotation. That's a key thing to be looking out for. That is your key, your tip-off that this is going to be a washer problem, that there is open space, again, between that region and the axis of rotation. Okay, so let's put in our rectangle. We're rotating it about the x-axis, so we need a rectangle that is perpendicular to that. So we will have a vertical rectangle right here. All right, so vertical is always the y values, so that is our radius y. All right. Okay, so I'm going to reflect our two curves. So our x to the 1/3 comes down here, and then our decreasing exponential function comes up like this, and then we can put in our two rings. All right, the bottom of the rectangle is touching the function that is closest to the axis of rotation. So there is our inner ring. So our inner function is right here. That is the inner function closest to the axis of rotation. And then up here at the top of the rectangle, that is on our decreasing exponential function. So that is the farthest away from the axis of rotation. So that is our outer ring. All right, so you can kind of visualize that rotation turning into a three-dimensional solid for volume. Okay, so let's set up our definite integral. Again, we have the elongated s. Our limits are given to us. And we will be always doing the outer function minus the inner function. All right, this is going to be a dx. All right, so we need, from 0 to 8, we need a pi y squared for our outer function, farthest away from the axis of rotation, and then minus another pi y squared. That is our inner function, closest to the axis of rotation. All right. All right, so let's keep going. I like to factor out the pi, so we put that out here. And then we need a y squared minus a y squared. See if I can squeeze in a dx. Oops, dx. Okay, all right, so again, our outer function, the top of the rectangle, farthest away from the axis of rotation, goes right here. So that is our 10e to the negative 0.1 x. And again, don't forget to square that. All right, our inner function, closest to the axis of rotation, that is right here. That is our x to the 1/3. All right, so there is our definite integral. For those of you with the newer calculators, you can punch that in just as is. For those of you with the older calculators, it is really nice to simplify this so it's easier to punch in. All right, so let's simplify. Again, we're going from 0 to 8. The pi is still out here. Here we have an exponent outside of a set of parentheses. So everything in there has to be squared. 10 squared gives us 100. When I raise one power to another, I multiply. So that gives me 100e to the negative 0.2x. And then over here, again, when I raise one power to another, I multiply. So 1/3 times 2, multiply tops and bottoms, gives me x to the 2/3. So there is our simplified definite integral right here. All right, so now you're all ready to go to Math 9. Try that right now. When you check your answer, you should have 1,193.34. And that is units cubed. That is a volume. All right. Let me know how you're doing. Thanks, calculus.